Look up at the night sky and find the faint, hazy band of the Milky Way stretching across the darkness. You're looking at our cosmic home, a vast spiral galaxy containing 400 billion stars. But here's something that might shock you. Despite all our dreams of exploring the universe, despite every science fiction story about intergalactic travel, we will almost certainly never leave this galaxy. Not in 1,000 years, not in 1,000,000 years, probably not ever. The universe has built walls around us, not walls of stone or steel, but walls of distance, time, and the fundamental laws of physics themselves. If you're fascinated by these cosmic realities that challenge everything we thought we knew, make sure to subscribe and hit that like button to help spread real science to curious minds everywhere. And one quick question: if you could have a conversation with your future self from 1,000 years ahead, what's the first thing you'd ask? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. To understand why we're trapped in the Milky Way, we first need to grasp the mind-breaking distances involved. Our nearest major galactic neighbor, Andromeda, lies 2.5 million light-years away. That number is so large it loses meaning, so let's break it down. Light, the fastest thing in the universe, takes 2.5 million years to travel from Andromeda to us. The light you see from Andromeda tonight left that galaxy when our ancestors were just beginning to use stone tools. But distance is only the first challenge. The universe isn't static, it's expanding, and that expansion is accelerating. Right now, Andromeda is actually moving toward us and will collide with the Milky Way in about 4.5 billion years. But every other major galaxy is racing away from us, and the farther away they are, the faster they're receding. Most galaxies are already moving away faster than we could ever hope to catch them. Let's put this in perspective with real numbers from actual observations. The Hubble Space Telescope and more recently the James Webb Space Telescope have shown us galaxies over 13 billion light-years away. But here's the kicker. Due to the universe's expansion, those galaxies are now over 30 billion light-years from us and moving away at speeds greater than light itself. Yes, you heard that right. Space itself can expand faster than light, carrying galaxies with it. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has mapped millions of galaxies and confirmed this cosmic expansion. Every galaxy beyond our local group, the small collection of galaxies gravitationally bound to the Milky Way, is destined to disappear beyond our cosmic horizon. In about 100 billion years, any civilization in the Milky Way will look out and see only darkness beyond our local group. But let's say we're optimistic. Let's imagine we could somehow build a spacecraft capable of traveling at 99% the speed of light, far beyond anything our current physics suggests is practical. Even at this incredible speed, a journey to Andromeda would take over 2.5 million years from Earth's perspective. Due to time dilation, the travelers would experience a shorter journey, perhaps 40,000 years. But that's still longer than all of recorded human history. And Andromeda is the easy target. It's the closest major galaxy, and it's moving toward us. Every other galaxy presents an even more impossible challenge. The Triangulum galaxy, the third largest in our local group, is 3 million light-years away. The nearest large galaxy cluster, the Virgo cluster, is over 50 million light-years distant. At 99% light speed, that's a 50 million-year journey from Earth's perspective. The energy requirements for such journeys are staggering. According to Einstein's special relativity, as confirmed by countless particle accelerator experiments at CERN and Fermilab, accelerating mass to near light speed requires exponentially increasing energy. To accelerate a single kilogram to 99% light speed requires energy equivalent to the entire power output of the United States for several years. For a realistic spacecraft weighing thousands of tons, you'd need energy equivalent to converting entire planets to pure energy. Recent studies by NASA's Breakthrough Propulsion Physics program and ongoing research at institutions like the Tau Zero Foundation have explored every conceivable method of interstellar propulsion. From fusion rockets to antimatter engines, from solar sails to theoretical warp drives, every analysis comes to the same sobering conclusion. Even reaching nearby stars within our own galaxy pushes the absolute limits of what physics allows. Intergalactic travel is exponentially more difficult. The Voyager missions, humanity's most distant space probes, provide a reality check. Launched in 1977, Voyager 1 is now over 23 billion kilometers from Earth, the farthest human-made object. But at its current speed of 17 kilometers per second, it would take over 70,000 years just to reach the nearest star, Proxima Centauri. To reach Andromeda at Voyager's speed would take over 40 billion years, 3 times the current age of the universe. But speed isn't the only barrier. Intergalactic space is not just empty, it's the emptiest environment in the universe. The space between galaxies contains less than 1 atom per cubic meter. That's a trillion times less dense than the air you're breathing. This cosmic void extends for millions of light years in every direction, an ocean of nothingness that makes the space between stars look crowded by comparison. Recent observations by the Cosmic Web Imager and studies of the intergalactic medium have revealed that this space isn't completely empty. There are traces of hot gas and dark matter. But these traces are so diffuse they might as well not exist for any practical purpose. A spacecraft crossing intergalactic space would be more isolated than anything we can imagine, unable to refuel, repair, or resupply for millions of years. The psychological and biological challenges are equally daunting. Humans evolved on Earth, adapted to its specific conditions. We require constant supplies of food, water, and air. We need protection from radiation, stable temperatures, and gravity for our health. Creating a self-sustaining environment that could last millions of years is beyond our current technology and possibly beyond what's physically achievable. Consider what we've learned from space stations like Mir, the International Space Station, and China's Tiangong. Despite our best efforts, these closed systems require constant resupply from Earth. They suffer from equipment failures, air leaks, and degradation over mere decades. Scaling this up to a million-year journey introduces problems we don't even know how to begin solving. The fundamental laws of physics themselves conspire to keep us trapped within our galaxy. It's not just that intergalactic travel is difficult, it's that the universe seems specifically designed to prevent it. Every breakthrough in physics over the past century, from Einstein's relativity to quantum mechanics, has only reinforced these cosmic barriers. Let's explore how the very fabric of reality builds walls we cannot cross. Special relativity, confirmed by thousands of experiments since 1905, sets the ultimate speed limit. Nothing with mass can reach the speed of light. The Large Hadron Collider routinely accelerates protons to 99.99999% light speed, requiring the energy consumption of a small city. Yet those final decimal places toward true light speed would require infinite energy, not just in practical amounts, but literally infinite. The equation is merciless. As velocity approaches light speed, mass effectively increases toward infinity. This isn't just theoretical, we observe it every day in particle accelerators worldwide. The Stanford Linear Accelerator, Fermilab's Tevatron, and CERN's Large Hadron Collider all confirm that no amount of energy can push massive particles to light speed. If we can't get a single proton to light speed with the most powerful machines ever built, how can we hope to accelerate a spacecraft? But let's explore what modern physics tells us about potential loopholes. The Alcubierre drive, proposed in 1994, suggests warping space-time to move faster than light without locally breaking the speed limit. NASA's EagleWorks laboratory has even conducted small-scale experiments, but every analysis reveals the same problem. Such a drive would require exotic matter with negative energy density, something that may not exist in the required quantities anywhere in the universe. Dr. Harold White at NASA refined Alcubierre's calculations, showing that the energy requirements might be reduced from the mass energy of Jupiter to merely that of Voyager. But merely is relative. We're still talking about converting 700 kilograms of matter entirely to energy and somehow channeling it into warping spacetime. And that's just for a small spacecraft, not the generation ships we'd need for intergalactic colonization. Wormholes offer another theoretical possibility. Solutions to Einstein's field equations, worked out by physicists like Kip Thorne and Michael Morris, show that shortcuts through spacetime are mathematically possible, but again, they require exotic matter to stay open. Every attempt to find or create such matter has failed. The Casimir effect demonstrates tiny negative energy densities between closely spaced plates, but scaling this up to a traversable wormhole may be fundamentally impossible. Recent work in quantum gravity, including string theory and loop quantum gravity, has only reinforced these limitations. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests that the information content of any region is limited by its surface area, not its volume. This places fundamental constraints on how much complexity, including spacecraft and their occupants, can be squeezed through any hypothetical spacetime shortcut. The quantum vacuum itself presents barriers. Empty space isn't truly empty, it seethes with virtual particles popping into existence and annihilating. The Unruh effect predicts that accelerating spacecraft would see this vacuum as a hot bath of particles. At the accelerations needed for intergalactic travel, this quantum friction would create drag and heating that no material could withstand. Dark energy adds another layer of impossibility. Discovered through observations of Type Ia supernovae by the Supernova Cosmology Project and High Z supernova search team, dark energy is accelerating the universe's expansion. Every moment galaxies get farther apart and the energy needed to travel between them increases. We're not racing against a static obstacle, but an ever-growing one. The integrated Sachs-Wolf effect, observed by comparing the cosmic microwave background to galaxy surveys, confirms that space itself is stretching between galaxies. The BOSS survey and Dark Energy survey have mapped this expansion in detail. Galaxies, more than about 16 billion light-years away, are already receding faster than light, not moving through space faster than light, but carried by expanding space itself. We could never catch them, no matter our technology. And if you want to dive deeper into this cosmic isolation and what the accelerating expansion means for our future, I highly recommend the book called The End of Everything, Astrophysically Speaking, by Katie Mack. She brilliantly explores how dark energy is gradually cutting us off from the rest of the universe, turning each galaxy into an island of light in an ever-growing ocean of darkness. It's a perfect companion to understanding why we're truly trapped in the Milky Way. The link is in the description and pinned on the comments. Time dilation provides false hope that turns to deeper despair. Yes, at 99.99% light speed, time dilation would make a journey to Andromeda feel like only 3,500 years to the travelers. But that's still 35 centuries of human generations living and dying in a tin can, and that's just to reach our nearest neighbor. More distant galaxies would require proportionally longer subjective times. The twin paradox isn't just a thought experiment, it's been confirmed by flying atomic clocks on airplanes and observing muons created by cosmic rays. GPS satellites must account for both special and general relativistic time dilation to maintain accuracy. Every confirmation of time dilation is another confirmation that while travelers might age less, the universe outside continues its relentless expansion. Radiation presents another fundamental barrier. Intergalactic space is flooded with cosmic rays, high-energy particles accelerated by supernovae, active galactic nuclei, and other cosmic catastrophes. The Oh My God particle, detected in 1991, carried energy equivalent to a baseball thrown at 60 miles per hour, all in a single proton. Such particles would penetrate any conceivable shielding. At relativistic speeds, even ordinary hydrogen atoms become deadly radiation. The interstellar medium, sparse as it is, would hit a near-light-speed spacecraft like a constant beam of particle radiation. The faster you go, the more deadly space becomes. Calculations show that at 99.9% light speed, the radiation dose would kill any biological crew in minutes, regardless of shielding. Thermodynamics imposes its own limits. The second law states that entropy always increases in isolated systems. A spacecraft traveling for millions of years would face inevitable degradation. No machine runs forever. No closed ecosystem maintains perfect recycling. Every system tends toward disorder, and the timescales of intergalactic travel guarantee that entropy wins. Recent studies of closed ecological systems, from Biosphere 2 to various space station experiments, show how quickly isolated systems degrade. Unexpected chemical reactions, material fatigue, and biological evolution all contribute to system failure. The Mars 500 experiment, simulating just a 500-day mission, revealed psychological and technical challenges we're barely beginning to understand. Quantum decoherence adds a subtle but fundamental barrier. Any quantum technologies we might develop for navigation, communication, or computation would face decoherence from interaction with cosmic rays and the quantum vacuum. Over millions of years, quantum information would inevitably degrade, potentially catastrophically for any systems depending on quantum coherence. Even if we could somehow overcome the laws of physics, even if we found magical propulsion that approached light speed, we'd face another set of barriers that might be even more insurmountable: the biological and technological realities of keeping humans alive for millions of years in the void between galaxies. Every long-duration space mission we've ever conducted has taught us the same humbling lesson. Space is trying to kill us in ways we're still discovering. Let's start with what we've learned from our longest space missions. Valery Polyakov spent 437 consecutive days aboard the Mir space station. Scott Kelly spent 340 days on the International Space Station, while his twin brother Mark stayed on Earth, providing NASA with invaluable data on long-term space exposure. The results were sobering: bone loss, muscle atrophy, vision problems, genetic changes, and psychological challenges we're only beginning to understand. The twins study, published in Science in 2019, revealed that Scott Kelly experienced changes in gene expression, cognitive decline, and DNA damage during his year in space. His telomeres, the protective caps on chromosomes, lengthened in space, then shortened rapidly upon return, potentially accelerating aging. His gut microbiome shifted dramatically. These changes occurred in just 1 year within Earth's protective magnetosphere. Now imagine millions of years in intergalactic space. Radiation is the silent killer. Earth's magnetic field and atmosphere protect us from cosmic rays and solar radiation. The ISS orbiting within Earth's magnetosphere still exposes astronauts to radiation doses 50 times higher than on Earth's surface. Mars missions will expose crews to even more. But intergalactic space? That's a radiation environment we can barely comprehend. The alpha magnetic spectrometer on the ISS has detected cosmic rays with energies that defy explanation. In intergalactic space, without any galactic magnetic field for protection, these particles would bombard any spacecraft continuously. DNA repair mechanisms that evolved on Earth would be overwhelmed. Cancer rates would skyrocket, mutations would accumulate. Over millions of years, radiation would destroy any biological crew. But let's say we solve radiation with some hypothetical shielding. We still face the closed ecosystem problem. Biosphere. 2. The ambitious experiment in Arizona from 1991 to 1993 attempted to create a sealed, self-sustaining ecosystem. It failed spectacularly. Oxygen levels dropped. Carbon dioxide spiked. Crops failed. Insects died off while others exploded in population. The carefully designed ecosystem collapsed in less than 2 years. The Melissa project by the European Space Agency has spent decades trying to create a closed-loop life support system. Despite sophisticated technology and biological engineering, they've achieved only partial recycling. Perfect recycling may be thermodynamically impossible. The second law of thermodynamics guarantees that some resources will always be lost as waste heat and unusable compounds. Consider the numbers. The ISS requires about 15,000 pounds of supplies per year for a crew of 6. That's with significant recycling of water and air. For a million-year journey, even 99.99% recycling efficiency would mean carrying impossible amounts of backup supplies. And that assumes no major system failures, no unexpected chemical reactions, no evolution of microorganisms into forms that break the recycling loops. Speaking of evolution, it's not just human bodies that would change over millions of years. Every microorganism on the ship would be evolving, potentially in dangerous directions. The evolution experiment on the ISS has shown that bacteria evolved differently in microgravity. E. coli developed thicker cell walls and increased antibiotic resistance. Over millions of years, our essential gut bacteria could evolve into something unrecognizable, potentially lethal. The psychological challenges might be even worse than the physical ones. The Mars 500 experiment locked 6 volunteers in a simulated spacecraft for 520 days. They experienced depression, sleep disorders, and conflicts. One crew member became so isolated he stopped participating in group activities. This was just 500 days with the knowledge they could leave any time. True intergalactic travelers would face millions of years with no escape. Studies of isolated Antarctic research stations, submarine crews, and solitary confinement show consistent patterns. Humans need variety, purpose, and hope. A journey where thousands of generations live and die without ever seeing the destination would create unprecedented psychological pressures. How do you maintain purpose when your great-great-great-grandchildren times 1,000 won't see journey's end? The technological challenges are equally daunting. No machine runs forever. The Voyager spacecraft, our longest operating deep space missions, are failing after just 46 years. Their plutonium power sources are depleting, instruments are shutting down, thrusters are clogging. By 2025, we'll lose contact forever. These are simple robotic probes. Imagine maintaining a life-supporting generation ship for millions of years. Material science gives us hard limits: metal fatigue, cosmic ray damage, micrometeorite impacts, and simple wear accumulate over time. The ISS requires constant maintenance and replacement parts from Earth. Its solar panels degrade. Its seals leak. Its electronics fail. NASA estimates the ISS can last perhaps 30 years total. Scaling up to millions of years isn't just a bigger challenge, it may be impossible with any materials we know. 3D printing and self-repairing systems offer hope, but face their own limits. Every recycling process loses some material. Every repair introduces potential failures. The ship would need to carry raw materials for millions of years of repairs, or somehow harvest them from the near vacuum of intergalactic space. Neither option is realistic. Power generation for millions of years poses another impossibility. Nuclear reactors require fuel that would deplete. Fusion reactors, if we ever build them, would need deuterium and tritium we couldn't replace. Solar panels are useless in the darkness between galaxies. Theoretical black hole power stations or dark energy harvesting remain pure fiction, with no path to reality. Recent studies of generation ships by researchers like Frédéric Marin and Camille Bellouffi have used Monte Carlo simulations to model population dynamics over centuries. They found that even under ideal conditions, genetic diversity degrades, social systems collapse, and technical knowledge is lost. Their models only extended centuries. The millions of years needed for intergalactic travel would amplify every problem exponentially. The minimum viable population for genetic diversity is estimated between 5,000 and 10,000 individuals. But maintaining this population for millions of years in a closed environment creates impossible resource demands. Every person needs food, water, air, and space. Every person produces waste. The ship would need to be impossibly large or impossibly efficient. While we've been discussing the challenges of leaving our galaxy, the universe itself has been actively making escape even more impossible. Every second that passes, the space between galaxies grows larger. This isn't just a poetic way of describing motion. Space itself is literally expanding, and that expansion is accelerating. The discovery of this cosmic acceleration earned the 2011 Nobel Prize in Physics, but for anyone dreaming of intergalactic travel, it was the ultimate bad news. The Hubble Space Telescope's observations of Type Ia supernovae in the 1990s revealed something shocking. Distant galaxies aren't just moving away from us, they're accelerating. The Supernova Cosmology Project and the High-Z Supernova Search Team independently confirmed that some mysterious force, what we now call dark energy, is pushing the universe apart faster and faster. Let's put this in concrete numbers. The current expansion rate, called the Hubble constant, is about 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. This means that for every 3.26 million light-years of distance, galaxies are receding an additional 70 kilometers per second faster. Andromeda, at 2.5 million light-years, should be receding at about 54 kilometers per second due to expansion alone, though its local motion toward us overcomes this. But here's the terrifying part. This expansion is accelerating. The Dark Energy Survey, using the Blanco telescope in Chile, has mapped millions of galaxies to trace this acceleration. The results are unequivocal. Dark energy makes up about 68% of the universe's energy density, and it's winning the cosmic tug-of-war against gravity. What does this mean for intergalactic travel? Every moment we delay, our potential destinations race away faster. Galaxies that are currently at the edge of our observable universe are already receding faster than light. We can still see them because we're seeing light they emitted billions of years ago, but any light they emit now will never reach us. They've crossed what's called the cosmic event horizon. The Sloan Digital Sky Survey has created three-dimensional maps of millions of galaxies, showing how they're distributed in vast cosmic webs and voids. These maps also reveal the universe's expansion history. Looking at galaxies at different distances and therefore different times in the past, we can see how the expansion rate has changed. The verdict is clear. Acceleration began about 5 billion years ago and has been increasing ever since. You might wonder, we can see our own galaxy's incredible scale and complexity. Why venture beyond it? Our Milky Way alone contains 400 billion stars, countless planets, and mysteries we've barely begun to explore. If you're curious about just how vast our galactic home really is, check out my video called "How Big is the Milky Way?" I break down the mind-blowing scales within our own galaxy that we could spend millions of years exploring. You'll discover that even being trapped in the Milky Way gives us an empire of stars vaster than we could ever fully explore. The link is in the description below and pinned on the comments. But let's continue with why even this vast kingdom will eventually become isolated. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang, with unprecedented precision. This map reveals the universe's composition: about 5% ordinary matter, 27% dark matter, and 68% dark energy. That dark energy percentage is growing, meaning acceleration will only get worse. Future projections are sobering. In about 100 billion years, all galaxies outside our local group will have passed beyond the cosmic event horizon. The local group itself, the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, will merge into one giant elliptical galaxy. This merged galaxy will float alone in an empty, dark universe with no other galaxies visible in any direction. The illustrious simulation, one of the most sophisticated computer models of cosmic evolution, shows how this isolation will unfold. Galaxies are currently arranged in a cosmic web of filaments and clusters, but dark energy will gradually tear this web apart. Clusters will disconnect from each other. Then galaxies within clusters will drift apart. Eventually, only gravitationally bound groups like ours will survive. This isn't speculative, it's the inevitable consequence of measured physics. The Baryon Oscillation spectroscopic survey has traced how sound waves in the early universe created a characteristic scale in galaxy clustering. By measuring how this scale appears stretched at different cosmic distances, we can trace the expansion history and project it forward. Every measurement confirms the same dark future. The cosmic event horizon is currently about 16 billion light-years away. Galaxies beyond this distance are already unreachable. They're receding faster than light, and nothing we could ever send would catch them. This horizon is shrinking in co-moving coordinates, meaning fewer and fewer galaxies remain within our potential reach. Every year, about 20,000 stars pass beyond this horizon, lost to us forever. The European Space Agency's Euclid mission, launched in 2023, is designed specifically to study dark energy. Its observations of billions of galaxies will refine our understanding of cosmic acceleration. But every refinement so far has only confirmed the basic picture. The universe is pulling itself apart, and there's nothing we can do to stop it. Even within our local group, the future is strange. Yes, these galaxies are gravitationally bound and won't be torn apart by expansion, but the merger process will be violent. When the Milky Way and Andromeda collide in 4.5 billion years, the night sky will be spectacular for millions of years, but eventually will settle into a single, aging elliptical galaxy with little new star formation. The James Webb Space Telescope has shown us galaxies as they were over 13 billion years ago, when the universe was young and compact. These early galaxies were closer together, interacting and merging frequently. That cosmic neighborhood is gone forever, stretched apart by billions of years of expansion. We're seeing the universe's youth, knowing we live in its isolating middle age. Redshift surveys reveal the universe's expansion history written in light itself. As space expands, it stretches the wavelength of light traveling through it. The most distant galaxies are redshifted so severely that their visible light is stretched into infrared. This cosmic redshift is a direct measure of how much space has expanded since the light was emitted. The Atacama Cosmology Telescope and the South Pole Telescope have measured tiny variations in the cosmic microwave background that reveal the universe's expansion history. These measurements, combined with supernova observations and galaxy surveys, all point to the same conclusion. Dark energy is real, acceleration is happening, and isolation is our cosmic destiny. As if the physical barriers weren't enough, we face another sobering possibility. We might be alone, or nearly alone, in our galaxy. The Fermi paradox, the puzzling absence of obvious alien civilizations despite the vast number of potentially habitable planets, suggests something called the Great Filter. This filter might be behind us, making intelligent life extraordinarily rare, or ahead of us, meaning civilizations like ours don't last long. Either way, it impacts our dreams of intergalactic travel. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. When Drake first calculated it, estimates ranged from one, just us, to millions. But 60 years of searching have found nothing. No radio signals, no megastructures, no obvious signs of intelligence. This silence is deafening. The Kepler Space Telescope revolutionized our understanding of planetary abundance. It found that planets are common. Nearly every star has at least one. The mission discovered over 2,700 confirmed exoplanets and showed that Earth-sized planets in habitable zones aren't rare. There should be billions of potentially habitable worlds in our galaxy alone. TESS, Transiting Exoplanet Survey Satellite, has continued this census, finding planets around nearby stars. The James Webb Space Telescope is now analyzing their atmospheres, searching for biosignatures, but so far every world seems sterile. No oxygen-methane combinations indicating life, no industrial pollutants suggesting technology, nothing but natural chemistry. The SETI Institute has conducted increasingly sophisticated searches since 1960. The Allen Telescope Array scans millions of radio channels simultaneously. Breakthrough? LISTEN, funded by Yuri Milner, is surveying 1 million nearby stars and 100 nearby galaxies. They've found interesting signals like BLC-1 from Proxima Centauri, but all have proven natural or human-made upon investigation. If intelligent life is common, someone should have spread across the galaxy by now. Even at slow sublight speeds, it would take only a few million years to colonize the entire Milky Way, a cosmic eye blink compared to the galaxy's 13 billion-year age. Yet we see no evidence of galactic colonization, no Dyson spheres harvesting star energy, no self-replicating probes, no galactic internet. This suggests several disturbing possibilities. Maybe life itself is extraordinarily rare. The jump from non-living chemistry to the first replicating cell might be so improbable that Earth is among the very few places it's happened. Laboratory experiments trying to recreate life's origin have produced amino acids and other building blocks, but never actual life. We might be cosmic lottery winners. Or perhaps intelligence is the rare step. Life might be common, but the evolution of consciousness, technology, and the desire to explore might be vanishingly unlikely. Earth's history shows that for 3 billion years, life remained microscopic. Complex multicellular life is only 600 million years old. Intelligence capable of technology has existed for a cosmic microsecond. Most disturbing is the possibility that the Great Filter lies ahead. Maybe civilizations like ours inevitably destroy themselves. Nuclear war, climate change, artificial intelligence, or unknown technologies might doom every species that reaches our level. The doomsday clock maintained by atomic scientists suggests we're always minutes from midnight. Perhaps no civilization survives long enough for intergalactic travel. Recent studies of Earth's climate history reveal how precarious habitability is. The Paleocene-Eocene thermal maximum 56 million years ago shows how quickly climate can shift. Venus might have been habitable billions of years ago before a runaway greenhouse effect. Mars lost its atmosphere and water. Maintaining a life-supporting planet for the billions of years needed to evolve intelligence might be incredibly rare. The phosphorus problem adds another constraint. Phosphorus is essential for DNA, RNA, and cellular energy, but it's rare in the universe. A 2018 study in Nature suggested that Earth might have unusual phosphorus abundance due to our particular stellar neighborhood. Without enough phosphorus, life as we know it cannot exist, potentially making habitable planets even rarer. If we're alone or nearly alone in the Milky Way, intergalactic travel becomes even more pointless. Why struggle for millions of years to reach another galaxy that's probably just as empty? The universe might be filled with beautiful galaxies devoid of anyone to appreciate them, cosmic art galleries with no visitors. The zoo hypothesis and other solutions to the Fermi paradox don't help our situation. Maybe aliens are hiding, watching us like animals in a zoo. Maybe they're too alien to communicate with. Maybe they've transcended physical existence. None of these scenarios help us leave our galaxy. We're still trapped, whether alone or quarantined. Recent discoveries make the paradox sharper. Oumuamua, the first confirmed interstellar object to pass through our solar system, showed that objects do travel between stars. If natural rocks can make the journey, why haven't we seen artificial probes? The detection of more interstellar objects like Borisov only emphasizes how empty they are of obvious artificial origin. The search for extraterrestrial intelligence has expanded beyond radio to optical SETI, looking for laser communications. The Breakthrough Starshot project proposes sending tiny probes to Proxima Centauri. But these efforts only underscore our cosmic isolation. We're shouting into a void that doesn't answer back. Astrobiology has found life in Earth's most extreme environments: deep ocean vents, Antarctic ice, nuclear reactor cores. This suggests life might be hardy once established, but it also shows that all Earth life shares common ancestry. We've never found a true second genesis, even on Earth. Life might be a one-time cosmic accident. The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee, lists the improbable coincidences required for complex life. A stable star, a rocky planet in the habitable zone, a large moon to stabilize rotation, Jupiter-sized planets to deflect asteroids, plate tectonics to regulate climate, a magnetic field to deflect radiation. Each requirement reduces the probability of Earth-like worlds. Even if simple life is common, the jump to complex multicellular life required the evolution of mitochondria, a one-time event where one cell engulfed another in symbiosis. This happened once in Earth's history, suggesting it's incredibly improbable. Without this energy revolution, life might remain forever microscopic. The temporal window for intelligence might be narrow. Stars increase in brightness over time. Earth will become uninhabitable in about 1 billion years as the sun grows hotter. Complex life has only existed for the last 600 million years. This gives a narrow window for intelligence to evolve before the planet becomes hostile. Let's talk about energy, the fundamental currency of the universe and the ultimate barrier to our intergalactic dreams. Every calculation, every proposed technology, every optimistic scenario crashes against the brutal mathematics of energy requirements. The numbers aren't just big, they're so large they transcend human comprehension and enter the realm of cosmic impossibility. Einstein's famous equation, E equals mc squared, tells us that mass and energy are interchangeable. This is both a promise and a curse for space travel. Yes, a small amount of matter contains enormous energy, but it also means that accelerating mass to high speeds requires exponentially increasing energy. The relativistic rocket equation is merciless. Approaching light speed requires approaching infinite energy. Let's start with fusion, our most promising near-term technology. The ITER project in France, humanity's largest fusion experiment, aims to produce 500 megawatts from 50 megawatts input. Even if we achieve perfect fusion efficiency, fusing hydrogen to helium only converts 0.7% of mass to energy. To accelerate a modest 1,000-ton spacecraft to 90% light speed would require fusing about 300,000 tons of hydrogen, but that's just the beginning. The Tsiolkovsky rocket equation shows that you need to accelerate your fuel too. Including the fuel to accelerate the fuel and the fuel to accelerate that fuel creates an exponential spiral. Realistic calculations show you'd need millions or billions of times your payload mass in fuel. For intergalactic journeys, you'd need to convert entire planets to fuel. Antimatter offers better efficiency, 100% mass-to-energy conversion when matter and antimatter annihilate. But antimatter might be the most expensive substance in the universe. Fermilab and CERN produce nanograms per year at costs exceeding trillions of dollars per gram. Creating the tons needed for interstellar travel, let alone intergalactic, would require more energy than our entire civilization produces. The Bussard ramjet concept proposed scooping interstellar hydrogen as fuel, avoiding the need to carry it. But interstellar space contains about 1 atom per cubic centimeter. At high speeds, this thin gas creates more drag than thrust. Recent calculations show that magnetic scoops kilometers wide would be needed, and they still wouldn't work for intergalactic space where density drops to 1 atom per cubic meter. Solar sails avoid carrying fuel by riding at light pressure. The Planetary Society's light sail missions have demonstrated the concept. Breakthrough. Starshot proposes using powerful lasers to push tiny sails to 20% light speed. But laser power drops with distance squared. Pushing sails across intergalactic distances would require lasers powered by entire stars, perfectly focused across millions of light years. An engineering impossibility. Black hole drives represent the theoretical maximum efficiency. Dropping matter into rotating black holes can convert up to 42% of mass to usable energy. Some proposals suggest creating artificial black holes for spacecraft power, but creating and controlling black holes requires technologies indistinguishable from magic, and you still face the rocket equation. Even perfect efficiency doesn't overcome exponential fuel requirements. Let's examine the energy scales more carefully. The Sun outputs 4 times 10 to the 26 watts. Capturing all of this with a perfect Dyson sphere would provide enormous power, but accelerating just 1 million tons to near light speed requires about 10 to the 30 joules, equivalent to the Sun's total output for several years. For a true intergalactic arc carrying a civilization, you'd need to harness multiple stars for millennia. The Kardashev scale classifies civilizations by energy use. Type 1 harnesses planetary energy, Type 2 stellar energy, Type 3 galactic energy. Intergalactic travel requires high Type 2 or Type 3 capabilities, but we're currently about Type 0.7. The gap between us and intergalactic capability isn't just large, it may be unbridgeable. Exotic proposals like vacuum energy extraction face fundamental limits. The Casimir effect demonstrates that vacuum energy exists, but extractable energy density is minuscule. Even if we could extract all vacuum energy from a cubic kilometer of space, it wouldn't propel a spacecraft far. The universe's energy density is dominated by dark energy, but it's uniform and seemingly unexploitable. Warp drives and wormholes don't escape energy constraints. Alcubierre's equations require negative energy density to warp space-time. The amount needed decreases with optimization but remains enormous. Recent calculations suggest that even microscopic warp bubbles would require planetary masses of exotic matter that probably doesn't exist. The thermodynamic limits are equally constraining. Every energy conversion has inefficiencies. Waste heat must be radiated. In the cold of intergalactic space, radiating heat becomes difficult. Spacecraft would need enormous radiators, adding mass that requires more energy to accelerate. The engineering spirals into impossibility. Consider the infrastructure needed. Launching from planets requires overcoming gravity. Building in space requires lifting materials or mining asteroids. Either way, the energy investment is staggering. The Apollo program, just to reach the Moon, consumed about 1% of US GDP. Intergalactic infrastructure would dwarf global economic output by factors of millions. Time makes energy problems worse. Storing energy for millions of years faces fundamental challenges. Chemical batteries degrade, nuclear fuel decays. Even hypothetical antimatter storage would face quantum mechanical limits. Any storage system loses energy to quantum tunneling, cosmic rays, and inevitable inefficiencies. Million-year storage might be physically impossible. The universe itself conspires against us through entropy. The second law of thermodynamics ensures that usable energy constantly degrades to waste heat. Over intergalactic timescales, every energy source degrades. Stars die, black holes evaporate, particles decay. The universe is on a one-way journey from low to high entropy, and intergalactic travelers would be racing against cosmic heat death. Recent studies of self-replicating probes, supposedly our best bet for intergalactic exploration, reveal more problems. Even perfect replicators need energy and materials. In intergalactic voids, both are essentially absent. The probes would need to carry everything for millions of years of operation and replication. The mass and energy requirements spiral beyond possibility. Beamed power, sending energy via laser or microwave, fails over intergalactic distances. Beam divergence means that even perfectly collimated light spreads over distance. A laser beam tight enough to be useful across millions of light years would require apertures larger than planets. Pointing accuracy would need to predict target positions millions of years in advance. Even if we somehow overcame every physical barrier, every energy constraint, and every biological challenge, we'd face a final, insurmountable problem: the complete breakdown of coherent civilization across intergalactic distances. Information, the glue that holds societies together, cannot overcome the light-speed barrier. Any intergalactic expansion would fragment humanity into isolated islands, each evolving independently until they no longer recognize each other as kin. Consider the communication delays within our own solar system. A message to Mars takes between 4 and 24 minutes, depending on orbital positions. The New Horizons probe at Pluto required 4.5 hours for signals to travel each way. The Voyager probes, now in interstellar space, take over 22 hours for one-way communication. These delays already create operational challenges that preview the impossibility of intergalactic coordination. To Andromeda, our nearest major galactic neighbor, a message would take 2.5 million years to arrive. A round-trip conversation would span 5 million years. In that time, entire species evolve and go extinct. The genus Homo has only existed for about 2.8 million years. Any message we sent to Andromeda would be answered by beings as different from us as we are from Australopithecus. The bandwidth problem compounds the delay. Interstellar and intergalactic communication faces inverse square law power loss. The Arecibo message, humanity's most powerful deliberate broadcast to space, would be undetectable with our own technology at distances of just a few hundred light-years. Across millions of light-years, maintaining any communication channel would require impossibly powerful transmitters or impossibly large receivers. Information theory, developed by Claude Shannon, sets fundamental limits on communication. Every channel has finite capacity determined by bandwidth and signal-to-noise ratio. Cosmic distances ensure that noise from cosmic rays, interstellar medium, and quantum uncertainty overwhelm signals. Error correction can help, but requires redundancy that further reduces already minimal data rates. The Deep Space Network, humanity's system for communicating with distant spacecraft, struggles with probes just light hours away. The 70-meter Goldstone antenna can barely maintain few bits per second connections with Voyager. Scaling to intergalactic distances, even with hypothetical kilometer-wide antennas and stellar-powered transmitters, might achieve only bits per year or century. Cultural and linguistic drift would make any received messages unintelligible. Human languages change dramatically over millennia. Old English from just 1,000 years ago is barely recognizable to modern speakers. Linear B, used 3,000 years ago, required decades to decipher. Messages crossing millions of years would be utterly alien, even if sent by humans. The coordination problem destroys any hope of unified civilization. Earth governments struggled to coordinate across time zones. The Roman Empire collapsed partly due to communication delays across mere thousands of kilometers. An intergalactic civilization would face delays millions of times longer. Central authority becomes impossible. Each colony would inevitably develop independent governance, goals, and values. Technological divergence would accelerate isolation. Each world would face unique challenges requiring unique solutions. Different resources, environments, and random discoveries would push technology in divergent directions. After millions of years, colonies' technologies might be mutually incomprehensible. Imagine trying to explain smartphones to ancient Romans, then multiply that gap by thousands. Scientific knowledge would fragment irrecoverably. Currently, science progresses through global collaboration and peer review. Arxiv and scientific journals disseminate discoveries within days. But with million-year communication delays, each world would develop independent scientific traditions. Discoveries would be repeated unknowingly. Theories would diverge. The unity of scientific understanding would shatter. The light cone problem creates fundamental limits on knowledge sharing. Each location in space-time has a past light cone, events that could have influenced it, and future light cone, events it could influence. Locations separated by millions of light years have barely overlapping light cones. They literally exist in different causal universes, unable to share experiences or coordinate actions. Computer networks illustrate the problem at smaller scales. Internet protocols struggle with satellite delays of hundreds of milliseconds. TCP/IP breaks down entirely for Mars missions. New protocols like DTN, delay-tolerant networking, help but assume delays of hours, not millions of years. No conceivable protocol could maintain coherent networks across intergalactic distances. Quantum entanglement offers no escape. While entangled particles correlate instantaneously, no information can be transmitted through entanglement alone. This no-communication theorem is fundamental to quantum mechanics. Every proposed quantum communication scheme either violates known physics or reduces to classical communication limited by light speed. Economic systems would completely break down. Trade requires feedback loops, supply responding to demand, prices adjusting to scarcity. With million-year delays, no meaningful trade could exist. Each world would be economically isolated, unable to specialize or benefit from comparative advantage. The efficiency gains that lifted humanity from subsistence would be impossible on intergalactic scales. Legal systems depend on precedent and consistency. Laws evolve through cases, legislation, and social change. But with isolated worlds developing independently for millions of years, legal systems would diverge beyond recognition. Concepts of rights, property, justice, and governance would become incompatible. There could be no intergalactic law, only isolated islands of jurisprudence. Educational systems would fragment human knowledge. Currently, global curricula ensure rough consistency in what humans learn, but isolated worlds would develop completely different educational traditions. After millions of years, beings from different worlds wouldn't just speak different languages, they'd think in fundamentally different ways, shaped by divergent educational philosophies. Artificial intelligence might seem to offer solutions. Immortal AI could maintain continuity across million-year journeys. But AI would face the same communication limits. Worse, AI systems evolving independently for millions of years might diverge even more dramatically than biological intelligence. They might become mutually incomprehensible or even hostile. The synchronization problem extends to basic definitions. Currently, atomic clocks maintain global time synchronization to nanoseconds, but relativity means there's no universal now across cosmic distances. Different worlds would have irreconcilably different time standards. Coordinating any joint action would be impossible when you can't even agree on when now is. Perhaps the most profound barrier to intergalactic expansion is biological. Over the millions of years required for intergalactic travel and colonization, humans wouldn't remain human. Evolution doesn't stop, and the vastly different environments of other worlds would drive our species to fragment into countless separate lineages, each adapted to their specific conditions, until we become strangers to our own kind. Evolution operates on timescales that make intergalactic travel look brief. Modern humans, Homo sapiens, have only existed for about 300,000 years. In just the last 50,000 years, populations adapting to different environments have developed distinct characteristics: skin colors, body types, disease resistances. Over millions of years of isolation, human populations would diverge into separate species entirely. The founder effect would accelerate this divergence. Each colony ship or world would start with a limited population, perhaps thousands or tens of thousands of individuals. This genetic bottleneck means each population begins with only a fraction of human genetic diversity. Random genetic drift in these small populations would quickly lead to different evolutionary trajectories. Consider what we've learned from island biogeography. The Galapagos Islands, isolated for just a few million years, evolved unique species found nowhere else. Madagascar, separated from Africa for 165 million years, hosts creatures that seem almost alien. Now imagine human populations isolated on different worlds for similar timescales. Different gravitational fields would drive dramatic physical changes. On a high-gravity world, humans would evolve shorter, stockier builds with denser bones and stronger hearts. On low-gravity worlds, we might become tall and willowy, with reduced muscle mass and cardiovascular systems adapted to lower pressure. The belters imagined in science fiction adapted to asteroid living hint at these possibilities. Atmospheric composition would reshape our basic biochemistry. Worlds with higher oxygen might evolve humans with different hemoglobin, altered lung structures, or modified metabolisms. Lower oxygen would select for more efficient oxygen extraction. Even slightly different gas mixtures would, over millions of years, produce fundamentally different respiratory systems. Radiation environments would cause rapid evolution. Worlds with weaker magnetic fields or closer to active stars would face higher radiation. Populations might evolve enhanced DNA repair mechanisms, darker skin with novel protective pigments, or even entirely new cellular structures to handle radiation damage. Some populations might develop cancer resistance unknown on Earth. The microbiome would diverge catastrophically. Humans carry trillions of bacteria essential for digestion, immunity, and even brain function. Each world's unique environment would select for different bacterial populations. After millions of years, humans from different worlds might have incompatible microbiomes, unable to eat the same foods, or even safely interact without causing fatal dysbiosis. Dietary differences would drive digestive evolution. Worlds with different available proteins, carbohydrates, and nutrients would select for different digestive capabilities. Some populations might lose the ability to digest Earth foods while gaining the ability to process alien biochemistry. Lactose tolerance evolved in just thousands of years. Imagine the changes over millions. Reproductive isolation would emerge quickly. Even if populations from different worlds could still meet, they might no longer be able to produce viable offspring. Chromosomal rearrangements, incompatible developmental timing, or mismatched sexual characteristics could create reproductive barriers. We would fragment into multiple species incapable of reunification. Sensory evolution would adapt to different environments. Worlds with different light spectra might evolve eyes sensitive to infrared or ultraviolet. Dimmer worlds might develop enhanced night vision or echolocation. Different atmospheric densities would alter hearing ranges. After millions of years, beings from different worlds might perceive fundamentally different realities. Brain evolution wouldn't stop either. Different challenges would select for different cognitive abilities. Worlds requiring more spatial navigation might evolve enhanced spatial processing. Harsh environments might select for faster reaction times or better pattern recognition. The human brain has tripled in size in just 3 million years. Similar dramatic changes would continue. Artificial selection and genetic engineering would accelerate divergence. Each world would likely modify their population to better suit their environment. Different colonies would make different choices based on their values and needs. Some might enhance intelligence, others physical capabilities, others longevity. These directed changes would quickly make populations incompatible. Epigenetic changes would accumulate even faster than genetic ones. Environmental stresses alter gene expression patterns that can be inherited. Different worlds' unique stressors would create different epigenetic landscapes. These changes, building up over generations, would fundamentally alter how genes are expressed, even if DNA sequences remained similar. Symbiotic relationships would evolve differently. Humans might develop obligate symbioses with local organisms, like how mitochondria became part of our cells billions of years ago. Different worlds might see humans incorporating different symbiotic partners, creating fundamentally different kinds of beings that couldn't survive without their unique symbionts. Sexual selection would drive populations in unpredictable directions. Beauty standards, mating preferences, and reproductive strategies would evolve based on each world's unique conditions and cultural developments. The peacock's tail shows how sexual selection can create dramatic changes. Human populations would experience similar but divergent pressures. Genetic drift in small populations would fix random mutations. Neutral or slightly harmful mutations that would be eliminated in large populations can become fixed in small ones through random chance. Each world would accumulate different sets of these random changes, creating unique genetic backgrounds that compound over time. Horizontal gene transfer, rare in complex organisms on Earth, might become common in extreme environments. Bacteria already share genes across species boundaries. Under severe selective pressure, mechanisms might evolve for humans to acquire genes from other organisms, fundamentally altering our genetic architecture. Life history strategies would diverge based on environmental stability. Stable worlds might evolve longer lifespans and slower reproduction. Unstable worlds might select for faster maturation and higher reproductive rates. These fundamental changes in life history would create incompatible developmental programs. The molecular clock of evolution ticks steadily. Mutations accumulate at roughly constant rates. Over millions of years, even without selective pressure, populations would drift apart genetically. Combined with selection, drift, and other evolutionary forces, humans would fragment into a constellation of related but distinct species. As we approach the end of our journey through the impossibilities of intergalactic travel, we must confront the ultimate truth. The universe itself is designed for isolation, not connection. Every fundamental force, every cosmic process, every law of physics conspires to keep galaxies and their inhabitants forever separated. We are not just physically trapped in the Milky Way, we are temporally, causally, and existentially isolated in our cosmic island. The observable universe contains about 2 trillion galaxies, according to the latest estimates from the Hubble Space Telescope and James Webb Space Telescope, yet we will never visit even one of them beyond our local group. Each galaxy is an island universe, forever separated by expanding voids that grow wider every second. This isn't a temporary condition we might overcome with better technology. It's the permanent architecture of existence. Dark energy, comprising 68% of the universe's energy density, ensures this isolation becomes absolute. The LCDM model, our standard model of cosmology, shows that dark energy's repulsive effect will eventually overcome all other forces except the strongest gravitational bonds. Galaxies bound in clusters will remain together, but clusters will become increasingly isolated from each other. In approximately 100 billion years, the cosmic event horizon will shrink to encompass only our local group. Every other galaxy will have receded beyond the point where its light can ever reach us. Future civilizations will emerge in a universe that appears to contain only one galaxy, their own, surrounded by infinite darkness. They'll have no way to discover the Big Bang, cosmic expansion, or the existence of other galaxies. This cosmic loneliness extends backward in time as well. The cosmic microwave background, currently our window into the universe's infancy, is redshifting toward undetectability. In about 1 trillion years, it will be impossible to detect, erasing the evidence of our cosmic origins. The universe is not just isolating us spatially, but temporally, cutting us off from both our cosmic past and future. The anthropic principle takes on new meaning in this context. We exist at a special time when the universe's history is still visible, when other galaxies still dot the sky, when the evidence for our cosmic story remains accessible. Earlier, the universe was too hot and dense for life. Later, it will be too cold and empty. We live in a narrow window where consciousness can comprehend its cosmic context. Recent observations of the cosmic web by the Dark Energy Spectroscopic Instrument reveal the universe's large-scale structure, vast filaments of galaxies separated by even vaster voids. These voids, some spanning hundreds of millions of light-years, preview our future, empty spaces that will expand until they encompass everything beyond our gravitational island. The Great Nothing, or Botha's supervoid, spanning 330 million light-years, shows us what most of the universe will eventually become. This nearly empty region contains few galaxies compared to surrounding space. In the far future, such voids will be all that remains, with island galaxies like ours separated by billions, then trillions of light-years of nothingness. Quantum mechanics adds another layer of isolation. The many-worlds interpretation suggests that reality constantly branches into parallel universes we can never access. Every quantum event creates new branches, exponentially multiplying realities. We're isolated not just from other galaxies, but from infinite versions of our own galaxy in parallel branches of the wave function. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that our three-dimensional reality might be encoded on a two-dimensional boundary. If true, our perceived separation from other galaxies might be even more fundamental. We might be information patterns on a cosmic boundary, with distance and separation built into the very coding of reality. Time itself conspires against intergalactic travel. The universe has an age, 13.8 billion years since the Big Bang. It will have an end, whether heat death, Big Rip, or Big Crunch. This finite temporal extent means there's literally not enough time for light to traverse the distances that cosmic expansion will create. Some galaxies will become separated by distances that light couldn't cross, even given infinite time. The simulation hypothesis adds an ironic possibility. If our universe is a simulation, the vast distances between galaxies might be a computational convenience, rendering only what's necessary, keeping civilizations separated to reduce computational load. The impossibility of intergalactic travel might be a feature, not a bug, designed to keep the simulation manageable. Fermi's paradox becomes less paradoxical when we understand these constraints. We don't see galactic empires because they're impossible. Each galaxy's civilizations, if they exist, are trapped in their own islands, just as we are. The universe might teem with intelligence, but each pocket of consciousness is forever isolated, unable to know of the other's existence. The philosophical implications are staggering. If consciousness is the universe's way of understanding itself, then this understanding is forever fragmented. Each galaxy's intelligence can only ever know a tiny fraction of the whole. The universe's self-knowledge is broken into countless isolated pieces that can never be assembled into a complete picture. Our cosmic significance shifts in this context. We're not potential colonizers of the universe, but permanent residents of the Milky Way. Our destiny is not among the stars of distant galaxies, but among our own galaxy's 400 billion stars. This might seem limiting, but it also means our galaxy, vast beyond comprehension, is our entire inheritance. The Drake equation must be reconsidered. Instead of asking how many civilizations exist in the universe, we should ask how many exist in our galaxy alone. The answer matters because these are the only civilizations we could ever potentially contact. The trillions of potential civilizations in other galaxies might as well not exist from our perspective. Recent CT efforts acknowledge this reality. Projects like Breakthrough listen, focus on our galaxy and nearby stars, not because we lack ambition, but because physics makes broader searches pointless. We're listening for neighbors in our cosmic city, knowing that cities on other continents are forever beyond reach. The mediocrity principle, the idea that Earth and humanity aren't special, takes on new meaning. We're typical in that we're trapped in our birth galaxy like every other potential civilization. Our isolation isn't unique, it's the universal condition. Every conscious species that has ever existed or will exist faces the same impossible barriers we've discussed. The universe's ultimate fate reinforces this isolation, whether through heat death in 10 to the Google years, the Big Rip in 22 billion years, or another ending. The cosmos will eventually become inhospitable to life everywhere. Our temporary moment of consciousness in the Milky Way isn't just isolated in space, but in time, a brief flicker of awareness in an otherwise unconscious cosmos. After confronting all these impossible barriers, the mind-breaking distances, the laws of physics, the biological constraints, the cosmic expansion that pulls everything apart, you might feel despair. We're trapped, isolated, confined to a single galaxy in an ocean of unreachable islands. But here's the profound truth that changes everything. Our prison is a paradise. Our isolation is what makes us precious, and our constraints give our existence meaning. Being forever bound to the Milky Way isn't a limitation, it's our cosmic inheritance, and it's more than enough. Consider what we actually have. The Milky Way contains 400 billion stars. If we visited one star system every second, it would take over 12,000 years to see them all. At a more realistic pace of exploring one system per year, it would take 400 billion years, 30 times the current age of the universe. Our galaxy isn't a prison, it's an empire vaster than we could ever fully explore. Recent exoplanet discoveries reveal the true richness of our galactic inheritance. The Kepler mission and TESS have shown that planets are the rule, not the exception. Statistical analysis suggests our galaxy hosts over 100 billion potentially habitable worlds. Each one is a complete world with its own geography, weather, possibly biology, unique puzzles that could occupy humanity for millennia. The diversity within our galaxy surpasses anything science fiction imagined. We've found hot Jupiters orbiting their stars in days, super-Earths with surfaces of diamond or water, rogue planets drifting between stars, planets orbiting binary stars like Tatooine. The TRAPPIST-1 system alone has 7 Earth-sized worlds. The variety within our single galaxy exceeds what most fiction places in entire universes. Being confined to the Milky Way grounds us in reality rather than fantasy. Instead of dreaming impossible dreams of intergalactic empire, we can focus on achievable goals. Interstellar travel within our galaxy, while extremely difficult, isn't impossible. Generation ships, suspended animation, or life extension could make journeys to nearby stars feasible. We can realistically dream of humanity spreading across our galaxy over millions of years. Our isolation makes us cosmically precious. If life is rare and intelligence rarer still, then Earth might harbor the only conscious observers in the Milky Way. We're not just one civilization among countless others. We might be the only witnesses to our galaxy's beauty. Every sunset, every scientific discovery, every moment of wonder might be unique in our cosmic neighborhood. This uniqueness brings responsibility. We're not just living for ourselves, but as representatives of what's possible in our galaxy. If we destroy ourselves through war, environmental collapse, or accident, we might be extinguishing the only consciousness the Milky Way has ever produced. Our survival becomes a cosmic imperative, not just a selfish desire. The finite scope of our galaxy makes complete understanding possible. Unlike the infinite universe, our galaxy is comprehensible. Future humanity could realistically catalogue every star, map every planet, understand every phenomenon within the Milky Way. We could achieve complete knowledge of our cosmic home, something impossible if we could spread across infinite galaxies. Being trapped together might save us from ourselves. If we could escape to other galaxies, humanity might fragment irreversibly, but confined to one galaxy, we're forced to eventually reconcile, cooperate, and unite. Our shared imprisonment might be what finally brings humanity together as one species with one destiny. The Milky Way's collision with Andromeda in 4.5 billion years isn't a catastrophe but an opportunity. Our local group will merge into one giant galaxy, doubling our real estate. While individual solar systems will rarely collide, the merger will trigger new star formation, creating fresh worlds for our descendants. Our prison will expand, giving future humanity even more to explore. Understanding our limits liberates us from impossible expectations. We're not failing to build an intergalactic civilization, we're succeeding at what's actually possible. Every probe we send to another star, every world we terraform, every colony we establish is a victory against the vast distances and harsh physics that constrain us. Our cosmic isolation makes every discovery within our galaxy more precious. When we find life on Europa or Enceladus, decode signals from another civilization, or discover new physics. These won't be routine events in a galaxy-spanning empire, but unique moments in our isolated pocket of consciousness. Scarcity creates value, and our isolation makes every discovery priceless. The artistic and cultural implications are profound. Confined to one galaxy, human culture won't fragment into mutually incomprehensible traditions. We'll maintain enough connection to share art, literature, music, and ideas. The works we create won't be lost to impossible distances, but can enrich all of humanity across our galaxy. Science benefits from our confinement. Instead of spreading our efforts across impossible distances, we can focus on deeply understanding our local universe. The James Webb Space Telescope, the upcoming extremely large telescopes, and future observatories can thoroughly study our galaxy and local group. Concentrated effort yields deeper understanding than scattered exploration. Our limitation teaches humility and wisdom. The universe has shown us our place, not as potential gods ruling countless galaxies, but as conscious matter confined to one galactic island. This humility might be what we need to survive and thrive. Hubris leads to downfall, accepting our limits leads to wisdom. The search for meaning becomes clearer when we accept our boundaries. Instead of seeking purpose in impossible expansion, we find it in perfecting our corner of the universe. We can transform the Milky Way into a garden of consciousness, a beacon of life and intelligence in an otherwise empty cosmos. Future technologies we develop won't be wasted on impossible intergalactic dreams, but focused on achievable goals. Fusion power, antimatter production, life extension, terraforming, artificial intelligence, all can be directed toward making our galaxy a true home for humanity and whatever intelligences we create or encounter. The story of humanity becomes more coherent when bounded. Instead of fragmenting across impossible distances, our narrative remains unified. Future historians will tell the story of one species in one galaxy, a complete tale with beginning, middle, and end. Our cosmic story has scope and limits, making it meaningful rather than infinite and therefore meaningless. As you look up at the night sky, don't see a prison of unreachable lights. See your inheritance, 400 billion stars that belong to you and your descendants. Every point of light in the Milky Way is a destination you or your children's children might someday reach. That's not limitation. That's abundance beyond imagination. We will never leave the Milky Way, but that's not a tragedy. It's a gift. It means we're home. It means we belong here. It means this galaxy, vast and beautiful beyond comprehension, is ours to explore, understand, and cherish. We're not trapped. We're embraced by spiral arms of stars that define the boundaries of our cosmic kingdom. The universe has given us exactly what we need, not infinite space that would dilute our existence into meaninglessness, but a bounded realm vast enough for endless discovery, yet small enough to remain coherent. The Milky Way is our cradle and our destiny, our prison and our paradise, our limitation and our liberation. So embrace our galactic confinement. Celebrate that we have 400 billion stars to explore, rather than mourning the trillions we'll never reach. Find joy in the fact that we're all in this together, one species in one galaxy, sharing one cosmic destiny. The universe has given us the Milky Way, and that's more than enough for any species to find meaning, purpose, and endless wonder. We will never leave the Milky Way, and perhaps, in the end, that's exactly as it should be. If you made it through this entire cosmic reality check, you're exactly who I make these videos for. Subscribe for more mind-expanding journeys through space and time, and please give a thumbs up. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. Time dilation. Why moving faster slows you down. In this video, discover the real science behind time dilation, Einstein's special relativity, and why astronauts, GPS satellites, and even you experience time differently depending on speed and gravity. See you there.